Just forgot to do that in Zoom. So I do recommend coming to class on Monday and then maybe taking the test after that. But if you're feeling 100% comfortable, then by all means, you can certainly take the test at your will. Your final exam will open up. It's scheduled for Thursday. It will open up on Wednesday. So I will open your final exams up on Wednesday and they will run Wednesday to Friday. So you'll have 3 days to take your final exam, to elect to take your final exam. Now, as a reminder, that means you have to sign up for the final before that. It is a little compressed timeline for me. So I am there will be, please don't even ask, like and the people who are here, I are the ones that really probably need to hear this. Please don't ask to have an extension on signing up for that final. I will need to start making those tests this weekend. And once that midnight Friday hits, that's it. That's the test that I'm making. So make sure to understand that. So the 4th exam closes on Tuesday night or Wednesday at noon. Tuesday midnight, so Wednesday midnight, Tuesday 11:59. It's been out. So you have all day Monday and all day Tuesday. You do not have till noon on Wednesday. All day Monday, all day Tuesday. That's it. Make sure you sign up for that final. If you have questions about signing up, I know some of you emailed me yesterday. Unfortunately, I didn't anticipate this, but I ended up it was awful, on calls from 8 a.m. till 5:30. No joke. I had one 20-minute break to eat lunch with my nephews who I was watching yesterday while working. So I did not get to your emails. Those of you asked me about kind of questions about signing up. It is my intent to get that to them today. But if you have any questions about signing up for that final or what you should sign up for that final, and you haven't emailed me already, please do. If you do not hear back, if you did email me and you don't hear back from me by today, somehow it got buried in 350 emails that I have to get through this morning. So email me again. That would be fine. Send out another notification, but it's my intent to get back to you by then. All right. So let's just recap. Let's make sure. Any questions on those logistics? 4th exam is on Monday and Tuesday. Final opens Wednesday, closes Friday at midnight. Okay.
I have a question real quick.
Yeah.
For the so the grade calculation spreadsheet, for the 3rd exam, there's not like at least the one I'm using. I'm wondering, is there an updated one?
Yeah. Yep. So there is an updated one for that 3rd exam under our course material, same place you got the first one. It's just been changed. So yeah, you can.
Okay, thanks.
No problem. All right. Other questions? And thanks for popping out, Nick. I gotta go grab my markers, but thanks for popping out because that would have been long to type. So if you have a question that would be too long to type, pop out of your microphone. Okay. So we were talking about image formation in mirrors and how mirrors cause light to reflect. Aiden is asking how much time you get on the final. I assume you mean the final. That'll be just a 2-hour exam. So the final exam, which is always slated for 2 hours, will be 2 hours. I always give you a half hour for tech difficulties, so it'll be open for 2 hours and 30 minutes. So that's normal. Okay. So we have 3 types of mirrors that we're introduced to. And all 3 operated on the behavior of reflection. So that idea of reflection, meaning the angle of incidence equals the angle of reflection. And that is dependent on the normal, so relative to the normal. So just like with our lenses, the angle of incidence is taken relative to the normal. The angle of reflection is taken relative to the normal. And so with a plane mirror, that plane as in plane, flat, the angle of incidence and the angle of reflection are the same as with all mirrors. And those light rays will reflect parallel if we have a perfectly plane mirror. So light rays parallel to the optical axis will reflect parallel. I'm just going to angle those light rays so you can see indeed that we get parallel rays of light on reflection. So we talked about that. Images in, images in plane mirrors are always upright. They're virtual. That's that virtual idea of being upright because we perceive the image. It's not really being formed on a screen. We couldn't put a screen anywhere to get that image. And the proportions are normal. So the geometry of a plane lens tells us that the distance plane mirror, the distance I am from a mirror is the same distance my image is from the mirror. So the object distance and the image distance are the same. The object height and the image height are the same. So that we went over and showed some pictures of that. A concave mirror that is bent, curved inward like a concave lens is converging. So it brings these rays of light to a common point. And we called that common point the focal length. I know you can't, or the focal point. And the distance is the focal length. I know you can't quite see that while I'm writing it, but I'll turn the lights back on. This again is based on the law of reflection. Rays of light coming in parallel are reflected down through the focal point. Rays of light coming in parallel at the bottom are reflected up through the focal point. So parallel rays of light are through the focal point. And we did ray diagramming to show that image formation. I'm not going to repeat that today. Couple of vocabulary on those concave mirrors. The focal length is the distance between the focal point and the mirror. And we said that was half what was called the radius of curvature. And the radius of curvature was if I took this semi-curve and I made a giant sphere out of it, giant circle, of course, is a sphere because it has dimension, then this radius of curvature would be the radius of that sphere. And that's an important property in image formation, as we saw when we drew those images. We saw that as we moved an object away from the mirror, the image changed size and location, similar to when we did it for a lens. So let's just recap what those properties were. I'll write them all up, I guess. So for a plane mirror, we get a virtual image. Okay, virtual image. And I'm going to say it's normal looking, which tells us that the object distance and the image distance are the same. The object height and the image height are the same. So that was our plane mirror idea. So concave, we moved it around, and I took that mirror and I moved it closer to Max and further from Max, and we saw the image change. And then we drew those ray diagrams. Again, you don't have to draw the ray diagrams, but it's a good base. You have access to that from the last lecture. So the concave mirror did two things. When the object was outside the focal point, we discovered that the image was real. So it was upside down. When we had the object outside the focal point, the image was upside down. As I moved the mirror closer to the object, so as I moved the mirror closer to the object, I used Max, we saw that as the object distance decreased, the image distance, when we did the ray diagramming, increased. But when we aren't going to worry so much about distance in our description because I want this to be very visual for you. But we saw that the object height increased. So as we got closer, the image you saw got bigger. We got closer, the image you saw got bigger. The location of that image we would have seen would have gotten further away from the lens or from the mirror. But let's just think about it from a visual perspective for our purposes. Now, one thing that is kind of cool is as we go inside the radius of curvature, so when the object distance is inside the radius of curvature, we get a large upright image. And that makes sense. As I move closer, we said that the image increases in height. We get a magnified, a bigger image. Inside the radius of curvature, the object and the image have a ratio greater than 1. It means that, should have been image, sorry. It means that the image is larger than the object. It's magnified. So we can use the radius of curvature to have a magnified real image. As we move outside, as we continue to move the object further and further away, as the object distance goes outside the radius of curvature, the image height relative to the object height is less than 1. It gets smaller, okay? It gets smaller and it moves towards the focal point. So it gets smaller and it moves towards the focal point. Why might that be useful? Well, remember when I killed the ants with my convex converging lens? You can also kill the ants with a converging mirror. So by the same principle that we talked about why the image gets really, really tiny the further away the object goes, and why it goes towards that focal point applies to the converging, in the case of a mirror, concave mirror. The rays of light get more and more parallel, and we know that parallel rays of light converge on the focal point. And if I'm using the sun as my object, that convergence is high energy. And we can indeed start a fire on a piece of wood with a concave mirror. All right, and how big the real image is, depends on where the object is relative to the radius of curvature. Inside the radius of curvature, it's big. Outside the radius of curvature, it's small. These are real images, The other thing the concave mirror did, I'll put it down here for now, was if I went inside the focal point, this is when I brought that mirror really close to Max. What happened? Well, the image flipped over. So we got a virtual image. We got a virtual image, and the image with height relative to the object height was greater than 1. The image was larger than the object. Okay, so it was a magnified virtual image. So why might a concave mirror be useful for us? I mean, if I have a concave mirror and I'm looking at it from far away outside the focal point, then my whole world is upside down. I'm upside down. That's not very useful. But if I get inside the focal point really close, then my image is upright, it's virtual, and it's really, really big. Why might that be helpful? Well, if I'm in the bathroom and I want to make sure that my hair follicles are healthy, or I want to put on makeup, or I want to, I don't know, fix my face, having a concave mirror lets me see a magnified image of my face. And so vanity mirrors, they're called in bathrooms, are concave mirrors. If you have one of those, you can look at it and you'll see yourself really big close up, but if you walk away from that mirror, eventually you'll get outside that focal point and you'll flip over and you'll see everything upside down. What else good uses are these for? Well, a surgical suite. So imagine you're in a surgical suite and a doctor really wants to shine a light really concentrated on the area of surgery so that they have a lot of light available to perform the surgery. So what do surgical suite lamps look like? Well, they're these concave hoods with a light kind of like this. So we have a concave hood, and then there's this light here in the middle of that hood kind of suspended. Well, why is that helpful? Well, this concave mirror of a hood is converging the light from this lamp. And not only is the light from the lamp heading in that direction, but from here it's all converging to a common spot. And guess what? That's where you're having surgery, on that common spot. Similarly, satellite dishes. Satellite dishes bring rays. They're electromagnetic rays. Let's pretend they're light rays for a moment. Light is part of the electromagnetic spectrum. In and converging them to that receiver that's in the middle of a satellite dish. That receiver is at the focal point. Okay, so lots of uses for this concave reflective material. All right, questions on that? So uses for enlarging images and having them virtual, uses for having a focal point and converging light. All right, I'm going to erase this so I have some space to write our last mirror. And that last mirror that we did not yet do the ray diagramming for is our convex mirror. So the convex mirror is the one that goes out, and although I don't have maps for you to look at, you can look at the, the computer or the rest of the room. Hopefully you can see that. What do we notice about the image in a convex mirror? Well, we said it's upright and it looks small. And whether I bring the mirror close or far away, the image still looks small. It looks less small as I bring it close, but it still looks small. So how does that manifest in the ray diagramming to explain some of that imaging? Well, first of all, convex mirrors are diverging, and this is where we ended on Monday. So we see that with a convex mirror, the law of reflection tells us that these light rays are going to spread apart, and we indeed see those light rays spreading apart. I am gonna, instead of drawing this, I'm gonna share with you our image formation in a convex mirror. And I do have this on, well, where is it? Don't understand why sometimes it does not show up for me. Let's just try this again. There we go. Okay, that's our light. Okay, so here is our convex mirror. We see that a parallel ray of light is reflected in line with the focal point. And this focal point has the same rules applied to it as the other mirror, okay? The focal point is 1/2 the radius of curvature. And that radius of curvature is as if I took this sphere and I made a giant circle out of it. So our parallel ray of light is reflected in line with the focal point. Our ray of light in line with the focal point is reflected parallel. And then in the case of a mirror, the ray of light, we didn't talk about this with concave, but it is in your images. that I posted, so I want to make sure I tell you about it. Remember in a lens, we had that ray that if it bisects the lens, it is unrefracted because it hits it at 90 degrees. Well, there's also a ray that hits a mirror at 90 degrees, and it will be reflected back at 90 degrees, so it'll fall back on itself. That ray is in line with the radius of curvature. Okay, so that's a third ray we can use. We only need the two to do our ray diagramming, which you're not required to do anyway, but that is what that third ray is that you'll see in your images. I want to make sure I mention that. It is in both the images for concave and convex. So we do the same idea where this parallel ray identified as the dashed green line, and this ray identified as the dashed purple line, as well as the red line, converge at a common point. And those are the same rays of light that when hitting my eye would be the same rays of light as if the object was at this location and this height. And so that's that idea of a virtual image. Now, the thing about a convex mirror is no matter where I place this object, we will always produce a virtual image, and we will always have it smaller. So for a convex lens, a convex mirror, it is diverging. It always produces a virtual image like a plane mirror. That virtual image is upright. We cannot put that on a screen. We cannot project it. We cannot take a picture of it. It's made up in our head, essentially. And it's always smaller, which tells us that the image height relative to the object height is less than 1. So it's always an unmagnified, a shrunken image. Now this leads to some problematic perception when using these mirrors. They have a nice advantage. One advantage of them, I'm going to go grab it again, is that rays of light, because they are spread out when they hit the mirror, rays of light coming from this side of the room are reflected to that side of the room. So if you were sitting on this side of the room, the people on that side of the room could see you in this mirror. They could not see you in a plane mirror, and they couldn't see you in a concave mirror. But because rays of light are spread out, the reflection goes towards that side of the room. Well, why is that helpful? Where do we see these mirrors? We see them in the corners of hospitals, or if any of you ever go by the fire station here in Menominee, over by Acoustic Cafe, there's one on a tree around the fire station. And why is that helpful? It lets us see around corners. How come? Well, because that corner is expanded in view now because rays of light from one corner are reflected past the wall to that other side of the hallway or the street. So they're really useful in that. But they do give you a goofy perception because it looks like things are really far away. And we talked about this when we talked about lenses. Why do images in these types of mirrors make objects look really far away? Well, the images is tiny, right? We do the ray diagramming either for a concave lens or a convex mirror. And we said that the image height is always less than the object height. It's the same for our diverging or a concave lens. Well, we have learned that certain height images on our retina represent certain distances away in our visual field, that mapping idea that we've talked about. And so I get this tiny image on my retina and I perceive that. I've learned, and my brain information says, well, then that object is far away. So I see it, I perceive it far away. This is kind of a problem. It's a catch-22. You have this expanded field of view, but your depth, how far you think things are, is all messed up. And where do we see that warning about that in particular? The rear view mirrors of cars. Not the rear view mirror, passenger side mirror of a car. So what is listed on that passenger side mirror of a car? It says, objects in mirror are closer than they appear. Well, that mirror is a very subtle convex mirror. It allows you to expand your visual view of the area that's difficult to see, the passenger side blind spot area of a vehicle. But because it's convex, it's producing a virtual small image, and our brain perceives that as being further away. So although you can see a wider range, you think the cars that are coming are a little further away. So when you turn, it's always important to check your blind spot, because when you turn, then you'll see that those cars approaching your blind spot are in fact closer than they seem to be based on the mirror. So our visual perception is a little messed up on how we've evolved and learned about tiny images on our retina. Okay, so that's it for mirrors. So I erase this and take my laser ray box down and get set up for our introduction to color. Any questions, either type them in. It's easier if you just unmute, but you do what you're comfortable with. Now we'll move on to our color description. I don't have any water today, so my pausing is going to be interrupted a little bit. Okay, let's talk a little bit about color. In our discussion of color, we're going to look at a couple of ideas, and we have to appreciate color perception. Again, back to the whole neuroscience, which is why I have so much fun teaching this. So why do we even have color perception? Well, we talked about the photoreceptors in the back of our eye, remember, in our retina. They're the cells that detect light, and that's what our brain then needs to perceive that there's an object there, that there's light in the environment. Well, there's two types of photoreceptors. I'm sure you have learned this in your past. This will ring a bell for you. I always spell words wrong. If you can't come up with it right away, we have what are known as the rods and the cones. And they are named that way because they look like rods and they look like cones. Okay, so that's just how they look. But they actually have very different characteristics. Rods are highly sensitive they can detect very low levels of light, but they can't distinguish between different types of light. So they're highly sensitive on intensity, and they have low sensitive, well, it's low sensitivity, I guess is a better way to use grammar, on differentiating wavelengths of light. Now, what are different wavelengths? Well, when we first introduced the idea of light, I showed you the electromagnetic spectrum, and that's really color. So they're very sensitive to the fact that light is happening, but they can't say what that light necessarily looks like, what color it is. They have no color sensitivity. Cones, on the other hand, have high color sensitivity. We'll talk about how they do that in just a second. But they're not so great at low levels. So not real high intensity sensitivity. Okay. Why does this matter? Well, you actually use this feature all of the time. So when we have very low levels of light, what happens to our visual environment as the world turns to dusk, as you're sitting in your dorm room and the lights are starting to, the sun's going down and it's getting darker and darker and darker? We start to sort of lose that color, right, of our environment. And furthermore, we actually get to a point, and some of you may experience this if you go out early morning hunting or fishing or hiking or running, or if you're in your room and you like to study in your room and you drop things a lot. I know it's a weird analogy. But what happens when we have sort of that low level light, where the world kind of just appears gray. If you try to look at something specifically, focus on something, what we call foveate. So try to put your fovea on the object you're interested in looking at. There's a point where the light level is low enough that you cannot see it at all. So if you're in that sort of dusk time, or your eyes are adjusting to the darkness in your bedroom, and they finally adjust and it's just dark in there, you can make things out, you can see things. But if you were to say drop your keys and you know they fell to your right and you look where they fell, you'll see them as you're looking in your periphery. But as soon as you physically foveate or look exactly where they are, they disappear. If you have not experienced that, try it tonight. It's really kind of fun and funky. Why do they disappear when I'm looking right at them? Well, that has to do with the idea of rods and cones. In the fovea, you only have cones, actually. In fact, you have only cones and everything else got pushed out of the way, and you're kind of heavy on the blue cones, just as an FYI. So you only have cones. Well, if you only have cones, they are not real sensitive to light. And you're at a light level where they're not sensitive to. But if you just let your peripheral vision search for those keys, you can see it. Well, in the periphery, you have a high density of rods. They are highly sensitive to low levels of light. So we're at a low level light situation. They actually see the light being reflected off the keys, and they perceive it, and they can process it and follow its pathway back to the brain. But the cones, they don't get any excitement. They don't release their rhodopsin. They don't send any information back to the brain. So in the case of the cones, they're saying nothing is there. And indeed, you don't see anything. In the case of the rods in the periphery, you do. Now, it's a common misconception that there are no colored cones in the periphery. That is not true. It is dominated by rods, but there is color in the periphery. And we know that because we see color in the periphery. So if I have a lot of bright light, I can see off to my left that there's a pink carp sitting there. It's painted pink on the top. And I can see that it's pink. I can't make out a great color of pink, but I can see that it's colored. So my rods, which are doing most of the work, can't really distinguish the color, but there's enough cones in there that I can tell that there is color. So rods and cones are both in the periphery, but dominated by the rods. Cones are only in the fovea. Okay, so there are no rods in the fovea. All right, we are going to focus on the cones. Focus on the cones and this idea of high color sensitivity. How do the cones get such high color sensitivity? Well, it turns out that that's because there are 3 of them. For most people, there are 3 of them. Those who are colorblind, one of the most common forms of colorblindness is that the colorblind individual is missing one of the types of cones. But there are 3 cones defined by their sensitivity. There are blue cones, red cones, and green cones defined by their sensitivity. And I want to share the screen with you again to explain what I mean by being defined by their sensitivity. So just as a reminder, we're dealing with color, we're dealing with light. We can ignore that slide for now. All right, so here is a graph of the different sensitivities of the 3 cones. So if I shine light on a blue cone, it is most active when I shine light that is within the blue ranges of the visual spectrum. So if we go back up here, we see that the blue range is between 400 and 500 wavelength. And we're in between this 400, 500, and we see a peak here at the blue. Similarly, green is at the more green range, and red is at the red range. Now, you'll notice on this screen, on this image, that blue cones are not only sensitive to blue light. If I were to shine a wavelength of light that had 500 nanometers, it would be sensitive. It just wouldn't be as sensitive. It gets really excited at this wavelength, less excited at this wavelength. So it's important to appreciate as we go to the color sensitivity that these cones are indeed sensitive to other wavelengths of light. Okay. So even though that's the case, we're going to use the model of light of only 3 colors. And we're going to see how we can perceive every other color just with thinking about light in these 3 primary colors. So we're going to model light as these 3 primary colors to associate with the 3 detectors of our visual system. Okay, so that's a model we're going to be moving forward with. So let's see what happens then and how we still can get this high color sensitivity even with our model of only 3 colors of light. I'm going to actually use them as I draw. Okay, so red light, we know, excites the red cones. Blue light, we know, excites the blue cones. And green light, we know, excites the green cones. Now, what happens if, hang on, the same person calls me each time on this day, I tell her what my class are. The same, back up. Red is we're gonna highlight red, blue, and green. Okay, let's start from there. So we're gonna have, what happens if I shine red light on an area in the visual environment? So can't see that yet, but here I am shining a red light on an area in your visual environment on the screen. And why do we see red? Well, I'm looking at the visual environment. I know that my retina is getting information that red light exists at that location in the visual environment. And so I see the red light. Pretty straightforward explanation. Now I have a blue light. The blue light is in a different location on my retina. And I see the blue spot because the blue cones are pretty excited and they're at that location on the retina. So I have red light at one location on the retina, blue light at a different location on the retina. I only have red light and I only have blue light. Those are the 2 lights I'm shining. What happens if I put the red light on the same location on the retina as the blue light? So the red light will excite my red cells. The blue light will excite my blue cells. Okay? So what do I see when I add the red light to the same location as the blue light? Well, then I see a whole new color. I see what we call magenta. So when I add red to blue, I see magenta. Is there a magenta light at that spot in the world? Nope, there isn't. It doesn't exist, yet I still perceive it. We're going to talk about that perception after we finish the color mixing. So when I add red to blue, I see magenta. What if I have a red light at one location in space and a green light at another location in space? Well, same thing. The retina is a map. The red light tells me, or my brain tells me that there's red at that location in the visual world because that's the cones that are active at that spot in the retina, green similarly. But what if I put my red light at the same spot as the green light? So my red cones and my green cones at the same location are active. Same location in space. I perceive yellow. So in the case of, there's no yellow light here, but my red cones are getting activated and my green cones are getting activated and they're at the same location in the world, and my brain says, oh, okay, well, that's yellow. Wonder why that is. We'll talk about that perception in a minute. But when I add red to green, I get yellow. What if I add green to blue? When I put green and blue at the same location, telling my brain I'm getting both blue and green at the same time, I get cyan. So adding green to blue gives me cyan. So what happens if I add everything together? If I flood the system with light, it's every possible light. It's red light, it's blue light, it's green light. It's all hitting at the same location. I keep adding light to the system and I get white. So we're going to go over those, write them down because you have to know this. This is what we call additive color mixing. We're adding light to the system. And the brain perceives this additive color mixing in a certain way. So when I take red light and I add blue light to it, I get magenta, what we call magenta. It is not purple, it is magenta. When I take blue light and I add green light to it, I get, oops, I'll use this. I get what we call cyan. When I take green light and I add red light to it, I got yellow. And when I added all three together, so red, blue, and green, I got white. Oh. This is our additive color mixing. You need to know these mixes, okay? Our additive color mixing. Now, this is different for those of you who are artists. This is different than paint. This is light mixing. Light mixing. We're going to talk about ink mixing, and paint is in part a chemical process. So this might be new for some of you. This is additive color mixing because we're adding light to the visual system. We're adding another color to the location in the visual environment that the brain then has to interpret. So why does it interpret these colors when I put red and blue together, or blue and green together, or green and red together, or red, blue, and green? Why does it interpret them that way? We have to go back to our spectral frequencies for our cones to get a good sense of that. So I'm going to pull us back to this image of the cones. Remember, blue was most active at the blue wavelength, green at green, and red at red. I'm going to take green and red, although this works for all of them. That one's the easiest, I think, to see. So I've put down here the actual visual spectrum. Now, when yellow light exists, remember, this is a model that we're using. So a yellow frequency of light is here in between. Here's our yellows. It's here in between 500 and 600, and it's closer to the 600, but it's between 500 and 600. When a light with a wavelength of close to 600, about 580, hits the visual system, what happens? Well, if I map this, it's all widen it just a smidge. I thought I had it, but I don't quite have it. I'm going to map this onto our spectrum here. So that's pretty close. When this color, this wavelength hits a green cone, the green cone gets active. When this wavelength hits the red cone gets active. And notice these two, the red cone and the green cone, are active in about equal amounts. Right here, they're active in equal amounts. And that falls in line with this color here. So when this color here hits the red and green cone, the red and green cone are excited in equal amounts. Well, what if I artificially excite them in equal amounts? If I shine a red spot on the retina, the red cone is active fully. If I shine a green spot in that same location, the green cone is active fully. And so those are equal amounts. And the brain says, well, I have equal amounts of red and green, which means I must be seeing yellow. So even though yellow wasn't there, I perceived it because I'm getting information about equal excitement of my red and green cones. So I've added information to the system and it gives me a new perception. If I highlight all of those, if I put red, green, and blue all together, that means that my cones are active, all of them in equal amounts. Well, that's the full spectrum, and the full spectrum is white. So we interpret adding all of those colors in as white. So additive color mixing is important for us to understand how we get this high sensitivity of color information. And we can use this red, green, blue model to describe how we perceive light, which is kind of cool. So we're going to stick with this red, blue, green model. Question. Yes, so Kyle is asking, are colorblind people missing a cone? They are missing a type of cone. So it's not like they have a reduced number of cones, but the gene that produces, and I am pretty sure it's the green cone, the gene that produces, I should know this, I get asked every year and then I look it up and I'm like, oh yeah, and then I forget by the next year, is missing. And so they don't produce that cone. Okay, they just don't produce that one. And so they don't have that additive mixing that we have. So they can't distinguish between greens and reds. And so there's no distinct, it sort of makes those two overlapping very different. So everything, so there's a sort of brownish color. Other questions? Okay, couple of vocabulary. Red, blue, and green are what we call primary colors of light. So these are our primary. Magenta, cyan, and yellow. These are our secondary. Okay, so these are our primary colors of light, and these are our secondary colors of light. So they're made by the mixing of multiple colors. When I don't have light, when I have an absence of light, when nothing is hitting my brain, my eyeball and subsequently my brain, that's when I interpret black, okay? So white is when everything hits me, adds all together. Black is when nothing hits me. Nothing is put into my visual system. And I interpret that as black. All right, let's play around with this a little bit more. I want you to predict what color will I see given this information in the following cases. And I'm just gonna have you predict them. I won't have you write them down, or I won't have you vote on them. So I'm gonna have you just predict them. What if I overlap yellow and red? So a yellow dot and a red dot. What if I overlap cyan and yellow? And the third one, what happens if I overlap magenta and green? So I'm gonna get these dot combinations up, and I want you to predict what happens when I overlap a yellow dot with a red dot, a cyan dot with a yellow dot, and a magenta dot with a green dot. And we're gonna follow the model of light of the primary colors being red, blue, and green. So you guys make those predictions, write them down on a sheet of paper. So you're actually making a prediction and committing to it, and we'll give it a test. Just have to get my color mixers up. Okay. Cyan, yellow, red, and I'm gonna need a magenta eventually. Of course, I picked magenta and green, so I have to change two different colors. Oh, well. There's green. Okay. So I'm going to turn the lights off. Hopefully you got those predictions done. And then we will, let's erase this quick. We'll talk about why the predictions manifested the way that they did. We test them. Okay. So the first was yellow and red. So I have a yellow dot. Okay. And I have a red dot. And we're going to overlap them and we see, we kind of just see yellow still. Interesting. You might argue it's a little orangey yellow, and we can talk about that in a little bit. So I kind of just see yellow. Okay, well, here's my cyan dot, yellow dot, and my cyan dot. And if I overlap them, I see, I get white. Right? So yellow and red just gave me yellow, maybe a little extra orangey yellow. Yellow and cyan gave me white. Now I have to change two of these. We have, turn on the flashlight. I can turn on the flashlight. Maybe not. Okay. Get myself a little white. We are going to have, come on. Come on. It's not liking me right now. It's not coming out. There we go. We have green and magenta. So here's my green light. No, that would be magenta. Here is my green. So I'm going to put green with magenta and I get white. All right. So see how you did on your predictions. And we will, let me turn my flashlight off. We will discuss why those predictions came to fruition. So we said with yellow and red, we kept yellow. With cyan and yellow, we got white. And with magenta and green, we got white. So those were our results. Why might that be the case? Okay, well, we can always break this back down to our fundamental primary colors. So if I have yellow, we know that yellow is made up of red and green. Now I'm going to add to it some more red, which is just red. So now I have red and green and red. Well, the brain then is getting information about red and green at the same place, which we know is going to interpret it as yellow. So it's two reds and a green. So that yellow was a little bit on the more red side, or what we kind of call orangish. So that's why this gave us a yellow, what we could say was heavy on the red. But yellow is fun. Or a little orangish, either one. Okay, well, what about cyan and yellow? Well, cyan, we know is made up of blue and, get all my colors in, and green. Yellow, well, that's made up of red and green. So now the brain is getting blue and green and red, and a little bit more green. And so what does it perceive? Well, when it gets everything together, it perceives white. And maybe in this case, I have a little greenish to that white because I have a little bit more green than everything else. Magenta and green? Well, magenta is blue, and if any of you have taken psychology, that would be the Stroop test. Magenta is blue and red, And then we have green, which is just green. And that was a little bit more pure white. Well, the brain is adding red and blue and green. So we're getting all of them. So mixing of colors with light, we can rationalize and deduce what we'll get if we break down our different primaries. All right. How is this related to what we see when it's raining and the sun's shining? A rainbow. Well, in that case, the sun really does have all frequencies of light, okay? And other things, the electromagnetic spectrum. But we can actually think about our fundamental model, the red, blue, green model, even in that case, because if we think about what you learned in kindergarten about a rainbow, right? It was red, orange, yellow, green, blue, violet, right? Indigo's in there, I suppose. And then if you have a double rainbow, it starts out as red, orange, yellow, and so on. Well, these are our primaries. What's between red and green? Yellow and orange. So as I dissociate my full spectrum, I actually can also model that as overlapping. Because when green and red overlap, they get yellows and oranges. When red and blue overlap, they get the purples, the magenta, and the violet, and the indigo, depending on how much red we have versus how much blue we have. We don't talk about so much that in between blue and green, but because those are just related. I think they're closer. So you see this movement through cyan in a rainbow. You definitely have cyan. So we can produce a rainbow just by overlapping these lights as well. That's kind of a nice model to remind ourselves of something we learned fundamentally. Okay, any questions on additive color mixing? Additive color mixing. But if we combine these two topics that we've done, additive color mixing with shadow formation. So let's imagine that I have a red light, point source of light. This is red. And I have a green point source of light. And when we did shadow formation, here's my blocker. And here's my screen. I'm bringing this back to the beginning. I'm going to do this a little bit quick because I'm noticing the time and I want to do subtractive mixing first. All right. So what happens? Well, we know if we follow our shadow formation model. Move this down. If I follow our shadow formation model, then this red ray makes it. This red ray makes it, and all the red in between don't. So everything above this line would be illuminated by the red light. Everything below this line would be illuminated by the red light. Similarly, my green light, that one makes it. That one makes it. So everything up here is illuminated by the green light, and everything down here is illuminated by the green light. So at the top, the red and the green light are both illuminating the screen. I should see yellow. Then just the red light illuminates the screen, which would give me red. Nothing illuminates the screen here. Neither light are getting through. So nothing we know is black. And only green gets through here. And both red and green get through to the bottom. So if I'm using rays of light, that have color, I should get some funky colored shadows. So let's test that. So here is my red light. Let me put it over there. Here's my green light. When they overlap, we know we get yellow. Now, these two lights are right and left of each other here. Let me do it this way. I'm going to put them on top, more on top of each other, so it's vertical. Okay, so there's our yellow. All right. If I put a blocker in front, what do we notice? Well, oh, I put it backwards. Red is actually on the bottom. Let me switch it so it matches our picture. I did it backwards. I apologize. All right, now red's on the top. Okay. Red's on the top, green's on the bottom. So we see that now with my shadow, yellow is at the top, like we predicted. We then have red, then black, then green, and then our yellow again. So our shadow formation can be enjoyably connected to our color mixing. And you want to pay attention to that. Okay. So we can do both on an assessment at the same time. Hint, 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 hint. All right. Another sort of fun thing about color and additive color mixing is we still have some limitations in our visual system, even though we can combine light colors together and get perception of other colors. Red and green and blue all make white. But our cones have a location in space. When I shine the red light at one spot and the green light at one spot, the red cones here said, it's red there. The green cones here said, it's green there. And that spatial dependence can be kind of fun to play with in terms of the visual system. So I have this white ball. Okay, so it should look white on the screen. But if I spin it, we see that the ball now is really a red, blue, and green ball. Try to spin it slow so you should see those three dots. Why is it white when it's alone, but red, blue, and green when I'm spinning it? Well, when it's stationary, it's flashing a red, a blue, and a green light really, really, really fast. And my visual system, my red cones at this location in space get red, and then right away they get green, and right away they get blue. And before they really have time to even tell the brain that they got red, blue, or green, the brain gets all that information at the same time. There's a time issue. But as I spin the ball, the red one flashes now at a different location than the blue one and a different location than the green one. And we can see that it's really three lights in this white light as opposed to just one. So that's kind of fun. I can't turn it around. There we go. All right. So that is enough on additive color mixing. Questions on that? Then we'll move to the second type of color mixing. Okay. So the other type of color mixing we need to talk about is subtractive color mixing. And this is when we start to also talk about colored objects, because subtractive color mixing relies on the fact that objects, and we're going to use ink for all you graphic communications majors, that ink is actually an object, right? It's a fluid object. And so those of you in graphic communications know that our primary colors in ink, are magenta, cyan, and yellow. I use brown for yellow. All right. What does it mean to have a magenta object or magenta ink? Well, we need to appreciate that this color magenta is magenta because we view it in white light, okay? So any color of an object is assumed to be viewed in white light, okay? And we'll get to that when we do colored objects under colored light and how colors seem to change on us. So a magenta object is viewed under a white light, okay? That's why we call it magenta. And the makeup of that object, the makeup of that ink is such that when white light or red, blue, and green shine down on it, this object reflects blue and red, and I see magenta because blue and red are in the same location, and it absorbs green. So a magenta object reflects red, it reflects blue, so those two things hit my eye and I perceive magenta, and it absorbs green, okay? So green is not reflected to my eye, and the only thing I see is magenta and blue, red and blue, so I see magenta. Cyan reflects blue, reflects green, and eats up red. So when white light, red, blue, and green, hit the cyan pot of ink, then, or any object, then blue and green are reflected to my eye. I perceive cyan, and red is absorbed. And similarly, yellow reflects red and green and absorbs blue. Now, this is the language I need you to use. We are using the model of light as three colors, red, blue, and green. And I know when you probably first learned about why colored objects are the way that they are, you said, well, a cyan, let's use yellow because probably didn't use the word cyan. A yellow object is yellow because it absorbs all other colors and only reflects yellow. That's actually not true. It can be true. It can absorb, it does absorb all the other colors and reflects yellow. But it actually also reflects blue, red, and green. So I want us to be understanding of that idea. And for our purposes, we are using the ray model of light, the color model of light that is only red, blue, and green. It's going to simplify your explanations, and it actually works really, really well. And so we do that all the time in science. Of course, we develop models. And so I don't want you to tell me something is yellow because it reflects all colors of light except yellow, because that's only half true. It also reflects red and green. So I want you to shift the way you describe colored objects and then subsequently colored objects under colored lights to the model that we're using of red, blue, and green. So keep that in mind. So this is how we're going to look at that. Now, if magenta is reflecting red and blue and absorbing green, and I take magenta and I put it really, really close, like mix it up with cyan. So I'm going to put those two together, but we can imagine the molecules are all intertwining with another. Well, they're still doing their same job. So magenta is still reflecting red and reflecting blue. And cyan is still reflecting blue and reflecting green. Now, because cyan also absorbs red, the red that is reflected from the magenta goes into the cyan. So it's reflected and immediately absorbed by the cyan that's intermixed with it. The green that is reflected from the cyan immediately goes into the magenta because magenta absorbs green. So the green that's reflected is immediately eaten up by the magenta. And the only thing left when I mix cyan and magenta is blue. So cyan plus magenta makes blue. Why is it called subtractive mixing? Because I'm taking away the colors to get the resultant. I'm taking away the green and the magenta, and I'm taking away the red in the cyan. I'm subtracting them out, and the only thing left is blue. So my eye gets blue. If I have magenta and yellow, again, they do their job. Magenta reflects red and blue. But that blue is instantly taken up by the yellow. The yellow reflects red and green. But that's instantly green is taken up by the magenta. And the only thing left over after all the subtraction, excuse me, is red. So I've subtracted the colors away to get red. Finally, if I mix yellow and cyan, well, the yellow reflects the red and green, but that green, or that red, excuse me, is eaten up by the cyan. Cyan reflects blue and green, but that blue is eaten up by the yellow. And the only thing left over is green. I've subtracted everything else out. So cyan and yellow make green. Now, what if I put them all together? Well, magenta's red is eaten up by cyan, and magenta's blue is eaten up by yellow. Cyan's blue is eaten up by yellow, and cyan's green is eaten up by magenta. And yellow's red is eaten up by cyan, and yellow's green is eaten up by magenta. So I'm left with nothing. I've subtracted everything out, and all three together give me black. And so that's the idea of subtractive color mixing. I'm taking away colors by them getting eaten up, absorbed by the other colors, and what's left over is the color that I see. Questions on subtractive color mixing? All right, so that's the idea of ink. We are going to use the principles of ink. So the primary colors of ink are magenta, cyan, and yellow. The primary colors of light are red, blue, and green. They're different. The reverse, the complementary, are the other. So the secondary colors of ink are blue, red, and green. And of course, the secondary colors of light are cyan, magenta, and yellow. Okay, that's subtractive color mixing. Now, how do I get colors of light? I showed you a red spot, I showed you a green spot, I showed you all these lovely colors of spots. How did I get them? Well, I got them through a process called filtering. So we're going to talk a little bit about filtering and what a filter does. So let's imagine I have a flashlight, and a flashlight has white light. Okay, so our white light, our model that we're going to stick to is that light is red, blue, and green. Red, blue, and green. All right, so red, blue, and green is coming out of this light. Now, let's imagine that I put a red filter over that white light. When I put a red filter over white light, I get a red spot. So what does that tell me that light, that filter, this film that I'm putting over there is doing? Well, if I get a red spot, it's telling me that red is coming through. If red is coming through, but yellow, green, and blue are not coming through, that means this filter is filtering out green and filtering out blue. It's taking away the green and the blue, and only allowing red to pass through. And this is where the term filter can be kind of a misnomer. A red filter doesn't filter out red. It allows red to go through. A red filter takes away green and blue. A green filter, so again, I have my red, blue, and green light in this white light, but if I put a green filter, well, what do we expect to happen? Green filter in front of a white light gives me a green light. So that tells me green is over here, which means I took out red and I took out blue. There I go with the Stroop test again. Took out red and I took out blue. What if I put a magenta filter on in front of my light? So here's my light again. We know we have red, blue, and green in that light. So this is the model I want you to use. And now let me put a magenta filter. So I have a magenta filter. And of course, I see a magenta spot. What does that tell you is happening? Well, magenta is red. I'm really stuck on that. Is red and blue. Oh my goodness gracious. All right, that's magenta. Magenta is getting through, which means red and blue are getting through, which means this filter just takes out green. So filters colors are not filtering out the color. Filter colors are allowing that color to pass through. And we have to be cognizant of when I have a secondary filter, it's what primaries are getting through. So I want you to make a couple predictions. What happens if I start adding filters on top of filters? So what will happen if I'm going to use these three because I already have them in my light boxes. So this is a red, and for those who may be colorblind in the class, this is a red filter. This is a green filter. And this is a magenta filter. Okay. What happens if I put a yellow filter in front of my red filter? And I put a magenta filter in front of my green filter. And I put a cyan filter in front of my magenta filter. So I want you to make those predictions. What happens if I take a red filter and then I put a yellow filter on top of it? What will I see? A green filter, I put a magenta filter on top, and a magenta filter that I put a cyan filter on top. And I'm going to add one more prediction for you. My black marker is dead because I keep them open so I can do my red, blues, and greens. All right. So this again is red, blue, and green. What happens if I take I'm going to switch these two. So I'm going to start with a yellow filter. And I'm going to then put on a red filter. So this one's red and this one's yellow. So these three ideas, and then what happens if I just switch the order? Does that make a difference? So make your predictions while I set up. And then we will see how you did. And I'm gonna put all my gas back on from my markers dry out. Oh, that's already toast. Okay. All right, so red is going to get yellow. Green is going to get magenta. Good. And magenta is going to get cyan. All right. That's cyan. Perfect. Okay, let's test them out. How you did. So our first one was red. So here's our red spot. It's reflecting. Here's our red spot. And I'm going to put over the red spot a yellow filter, and I see, I see red. Fun. Okay, so then I have green, and I'm going to put over a magenta filter, and nothing. I blocked. There's nothing. I know you have to trust me that I'm actually doing what I said I'm doing. And then I have magenta, and I'm going to put a cyan filter, and I get blue. Very cool. Blue. And now I'm going to have yellow, which I forgot to pull out. Well, let's hold off on that because I'm looking at the time. Let's talk about it. Hopefully you got the predictions right. If not, that's okay. That's how we learn. All right, so my red filter, well, we said it took away the blue and the green, so now I only have red here. Yellow filters, well, if I see yellow on the opposite side of a filter, that must mean red and blue got through. No, it doesn't. It means red and green got through. Well, I don't have green to get through, but I do have red. So red can indeed get through, and I saw my red. So the red filter took out the blue and took out the green. The yellow filter would have taken out the blue, but I didn't have blue anyway, so it just let the red pass through. What about this one? Well, the green filter lets green through. So green is on this side, takes out the blue, and takes out the red. A magenta filter, well, that lets red and blue through. I don't have any red and blue to get through. It takes out the green, and I'm left with nothing. A magenta filter, well, that takes out the green, and it lets red, and blue through. It's magenta. Cyan, well, that takes out red. Normally, green and blue would get through. There's no green, so only blue gets through. And I'm left with blue on this side. Now, what if I had reversed the order? Well, if I had reversed the order, yellow would let red and green through. It would have taken out the blue. So between the filters, I would have indeed had yellow light, red and green. But as soon as I hit the red, my green gets taken out, and I'm left only with red. And so the order of the filters do not matter. All right, fun with filters. We do have one more topic, and that is colored objects under colored lights. And it's too fun not to do it. Super fun. We will do that on Monday. I will also right now, while I'm in the room, do a mini lecture on it. And so I'll use the colors to do that, which we will also cover on Monday. But if for some reason you want to start your test earlier and you want to get that content before Monday, you can watch the mini lecture. I'll post that with this material. So that is it. Colored lights and colored objects are so much fun. I find so much fun in them. So lots of fun with color. All right, that's it for today. I will stick around for any questions, and hopefully the video was okay since I don't have a camera adapter anymore. And we will go from there. Have a great weekend. Be safe. Wear your masks. All right, and if anyone has any questions, unmute yourself. Ian, you're my sole survivor. I know you're like, oh, you left.